Hello everyone, I thought we'd start today's lesson, chapter 20.2, the Doppler Effect, just with something just to think about by Bill Bryson in his Short History of Nearly Everything book. Every atom you possess has almost certainly passed through several stars and been part of millions of organisms on its way to becoming you. We are each so atomically numerous and so vigorously recycled at death that a significant number of our atoms, up to 1 billion for each of us, it has been suggested, probably once belonged to Shakespeare. 1 billion more each came from Buddha and Genghis Khan and Beethoven and any other historical figure you care to name. So we are all reincarnations, though short-lived ones. When we die, our atoms will disassemble and move off to find new uses elsewhere as part of a leaf or other human being or drop of dew. So on that note, we'll start the Doppler effect. But before we do, just a quick quiz to get you warmed up. So the nearest star, other than the Sun, is Proxima Centauri. It has a parallax of 0.76 seconds of an arc, or arc seconds you can call it. Calculate its distance from the Earth. So A in parsecs, B in light years, and C in metres. So give that a go, and then we'll just quickly look at the answers. Hopefully you'll have got them, and then we'll start looking at Doppler. So press pause, and when you're ready, press play and we'll start again. So here are the answers. Hopefully you got there without too much trouble, but as ever, if you need a bit more help, let me know. Okay, the Doppler effect. Now you would have heard of the Doppler effect, I would hope, from GCSE. The idea that frequencies of sound or wavelengths of sound vary depending on the observer, and everything absolutely has to be compared to the observer. There's an equation to look at, and as you can see, it is just here. So we've got delta lambda over lambda is roughly, but for our intents and purposes we can put equals, roughly equal to delta F over F, which is roughly equal to V over C. So there's an element of approximation here, but it roughly works, and it's absolutely good enough for what we need. So we've got the delta sign, so that refers to the change in, which we'll come on to in a moment. So that's for delta lambda and delta F. Lambda, same symbol as usual, which is our wavelength, measured in meters, and frequency measured in hertz. V and C. Now, C generally is given the speed of light, so 3 times 10 to the power of 8, which we're using in the worked example in a moment. Sometimes, and for part of your homework actually, you've got C being used as the speed of sound. So it's either the speed of sound or speed of light. So most of the time in this topic we do talk about light, so 3 times 10 to the power of 8. And V is what we call the recessional velocity. So how fast the thing, probably a star or a galaxy, is moving towards or moving away from us. The values of lambda or F frequency are always going to be the actual values, the ones that you would expect to see in a laboratory, in a lab. When you look at a star, if it's moving away from you, the frequency of light gets stretched. If it's moving towards you, the frequency of light or the wavelength of light gets compressed. And that then gives rise to a difference. So what we're doing is we're looking at two values of lambda or two values of F, wavelength and frequency, and we're comparing them to the wavelength or the frequency as measured in a lab. So if we now just take a look at this diagram down here, you'll remember from previous videos that there's a series of dark lines, and each dark line works with another dark line probably to make a pattern, and that pattern corresponds to a particular element, so hydrogen, helium. It has its own fingerprint of a pattern. So as you can see, there are two other diagrams, one above and one below. And if we just focus on this slightly wider line, if it's red shifted, it moves towards the red end of the spectrum. If it's blue shifted, it moves towards the blue end of the spectrum. If something is moving away from us, we call it red shifted. If something moves towards us, we call it blue shifted. And it can be compared to a siren going past or a motor car making that meow sound. That nyeh, as it approaches us, the pitch increases because the wavelength decreases, and the meow sound because the wavelength gets longer, which gives the pitch a slightly lower tone. So as it approaches us, high pitch, and then as it leaves us, slightly lower pitch. And the same is said with light. So something's moving towards us, the waves shorten, and that gives us the blue, slightly blue colour. If it's moving away from us, because the wavelengths are getting stretched, then they're moving ever so slightly towards the red end of the spectrum. And as we'll see in a second, the difference in wavelength that we see is extremely tiny. So let's look at our worked example. So in a laboratory, an absorption line of hydrogen is observed at a wavelength of 656.4 nanometers, so times 10 to the minus 9. In a distant galaxy, the same absorption line is observed at 658.1 nanometers. So you can see the change there. It's very, very small. Calculate the speed of the galaxy and state whether it's moving towards or away from the Earth. So first of all, we're going to calculate the change in wavelength. So it's literally one minus the other, so 1.7 times 10 to the minus 9, or 1.7 nanometers. The wavelength observed from the galaxy is longer than the wavelength in the laboratory, so the galaxy must be receding, it must be moving away. The spectral line has been red shifted. So part 2, the Doppler equation. So we don't always use all of the equation, so we haven't got anything to do with frequency, so that bit can disappear. So delta lambda over lambda is roughly equal to V over C. So just rearrange it to find out what that speed of the galaxy is. So now we've got the speed of light, 3 times 10 to the 8, multiplied by our change in wavelength, and then we're dividing through by 656.4 nanometers. Now, one thing to be careful of is choosing the right one, and we're always after the one that you've got in the laboratory. It's never the one that you've observed. And then whack it into a calculator, and that will give you an answer, which in this case gives about 780 kilometers per second. And just here I've got another worked example, so I won't go through this one, but feel free to press pause and play again when you are ready. Okay, hopefully you've had a look at that one. Just a couple more questions for you to have a go at. So again, press pause, and once you've had a go, press play, and then we'll look at the answers on the next page. Okay, so for question 2A, the answer was 2 times 10 to the 6. For B, 9.53 times 10 to the minus 2 centimetres. And C, 5.11 times 10 to the 6. And then the star could be rotating another object. So that's pretty much it for the lesson today. It's certainly worthwhile reading 20.2, the Doppler Effect, in your book. Figure 2 goes through the meow in a bit more detail. What I'd like you to do, please, is answer the summary questions, which I will flash up on the video now. So if you can work your way through those, and then of course check your answer with the back of the book, please. And then to hand in, I have got some links that I'll put on Show My Homework for you to attempt. And when handing them in, can you please make sure you upload them as a PDF file, because that makes it easier for me to be able to give you feedback directly without having to faff by turning JPEGs into a file. If you can't turn it into a PDF, can you at least give it to me in a Word document? Thank you very much, and hope you're well, and see you soon.